Okay, and welcome back to the channel. Thank you very much for joining the stream, and we will get started. So today we continue our study of tensor analysis. By the way, actually two streams today. So right now we're doing the tensor stream, and this evening, starting at 7 p.m. So right now here it's about 2 p.m. So at 7 p.m. there will be a complex variable stream. So there's that. Welcome. You're welcome to join there. So when it comes to tensor analysis, okay, tensor analysis was the dominant language of differential geometry, and it still is the dominant language in some subjects of theoretical physics, such as general relativity, and also in engineering, such as fluid mechanics, just continuum mechanics in general. So those are perhaps the most well-known areas of applications of tensor analysis. Our goal, however, is a little bit different because there is an upcoming session, live session at August 8th on information geometry. So information geometry is a relatively new, I mean, it's not that new, but still relative to the areas I just mentioned, and perhaps in terms of well-knownness, okay, also. So information geometry is the study of statistics, probability, and machine learning algorithms using the method of differential geometry. So it's a very exciting field. And right now it's still very much in active research, an area of active research. So it's a very exciting stuff. And the goal is to reason about, the goal is to reason geometrically about the power, the limitations of various data analysis, machine learning algorithm. So it has been shown to some success. For example, you might have heard of the algorithm in statistics called the EM algorithm. The full name is expectation maximization algorithm. It's a classic example of a well-known statistical algorithm being demystified from a geometric perspective. Yeah, the EM algorithm has a geometric interpretation, so that's pretty cool. And the hope is that we can do the same for other kinds of algorithm. And so this is a very active area of research. And to quote one of my professors on working on the subject, who actually publishes papers on information geometry, like he told me that it is very difficult to recruit graduate students in this area. Now, first of all, this is completely beyond the scope of undergraduate study. Okay, I don't think, perhaps it is possible, but I think it is still at this in the next, at least in the 10 years or so, it's very unlikely to see a course on information geometry at the undergraduate level, simply because of the amount of prerequisites required is quite heavy. But even though it is, in my view, some of the essential ideas of information geometry can still be communicated to people with only backgrounds of advanced calculus, meaning multivariable calculus, okay? Multivariable calculus, linear algebra, and probability. I think it is still possible. And which is the expected prerequisites, for the upcoming stream on information geometry on August the 8th. Okay, I will not assuming anything beyond that. I will not, of course, not assume any prior knowledge of differential geometry, topology, all of those things. Okay, we will start from assuming the audience has a reasonable command of basic calculus, basic multivariable calculus, as well as linear algebra and some probability. And in the course of preparing that stream, I noticed that information geometry still uses a lot of classical tensor analysis, and this is kind of a review for me, because I'm not a complete beginner when it comes to tensor stuff. I studied this about like 10 years ago, but later on, because of I haven't worked with this stuff quite often, so my knowledge kind of atrophied. Okay, so this is why I'm doing a revisit of that stuff. So I sort of expect what topics are coming next and whatnot. And speaking of that, we'll be assuming planned classical information. No, nothing. No. I would just, as I said, I would just assume a knowledge of probability, basic probability. You've seen, for example, Gaussian distribution, things like multinomial distribution. Okay, what's the parameter? And linear algebra and calculus, multivariable calculus, and nothing beyond that. Okay. And the goal is to introduce the basic ideas of information geometry and do some actual math. Okay, not the idea. It's a difficult balance, right? So on one hand, I would like to introduce a basic idea and see one concrete example, so audience can walk away with some actual math. Okay, not just a very high level knowledge of what this is about. Okay, perhaps this is where this is useful. Of course, that's good to have some big picture in mind. But I wish the audience, the plan is that the audience can walk away with that stream to do some actual computation. Okay, that's pretty much all the stuff. Okay, without any exaggeration, all the material on this channel are organized according to that principle. Okay, I don't want my audience to walk away with only a very vague sense of knowledge, because sometimes it can be illusionary. You feel like you know that, but well, if you can't crunch out the numbers, you can't really claim you know that, don't you? Right? Do you? Right? Can you? Right? So that's the idea. So that's why we're keeping our boots firmly on the ground while keeping the vision high in the sky. So that's the idea. All right. So anyway, enough about philosophy. So where are we now? Or where are we now? We already had 3 sessions on tensors so far. As you can see here on my left, you can see there is a stream on the 23rd. There was a stream on the 23rd, the 24th, and the 25th. So I was doing tensors 3 days in a row. Well, yesterday was a Sunday. I didn't have time, so today we're coming back. So where are we now? Okay, so where are we now? So on the very first one, just do a quick rewind. Okay, on the first one, we introduced the summation notation, and mostly it's just a summation notation. And use the summation notation to revisit some classic notions in linear algebra, such as matrix multiplication and determinants, and they can all be expressed in terms of index, or actually summation notation. That's the first one. And the second one is actually where we got to the definition of tensors. So the first one is purely notational, and the second one is we actually introduced the notion of tensor. And we did that in a motivated fashion, okay, because the actual definition looks a little bit scary. Okay, so we did that in a motivated fashion. But basically, what we managed to arrive at the end of the second stream is to define tensors as multi-index arrays that transform in a certain way under coordinate transformation. Okay, so that's the definition, which looks, if we don't do all the examples earlier, this would makes no sense. Right? But here, I think this now it's fair to just proceed with that definition, okay? Because we did enough preparatory work in those 2 streams. So this is the definition of tensor, which we adopt throughout the rest of our study. A multi-index array that transforms in a certain way, in this way. And in this transformation is not mysterious at all. It is the idea of invariance, because tensors are supposed to represent a quote-unquote geometric object. Think about a vector. A vector is a special case of a tensor. Yeah, think about a vector. Think about a vector like an arrow living in a space. Right? And that's that's an object on its own. Its properties should not depend on which coordinate system you choose to study it. Okay, so really it's that simple, right? So the vector itself is an invariant. And there are other kinds of invariants as well. Your data science engineer, big fan of Ben Weil. Thank you so much. Data science engineer research. Your videos have been essential to development of papers written. Thank you. Thank you. I'm really glad. So I was saying that tensors are supposed to represent invariance. And actually, the final goal, I mean the big goal of this series, it's said in the title, towards curvature. Curvature, think about the curvature of a surface. That's a geometric quantity as well. There's a geometric notion. It should be how curved a surface is, should not depend on what coordinate system you choose to study it. Right? But the thing is, we like coordinate system in geometry. Most of the time, we do like coordinate systems because they make the calculation so much easier. Right? Think about going back all the way to Euclid, the days without coordinate system. Sometimes you have to come up with extremely ingenious construction to prove simple propositions without coordinate systems. So coordinate systems are great. We don't want to do away with coordinate system. But at the same time, by introducing coordinate system, you introduce extraneous information. You introduce extraneous information. So let's say you derive an equation using coordinate system about a geometric object. Right? Let's say that's what you got. But at that point, you have to decide whether this result you obtained is an actual property of the geometric object that you study, like a curve or surface, or is it simply an artifact of the coordinate system being chosen? If the latter is true, then the result would not be very interesting, because somebody else could have easily chosen a different set of coordinates and your result would not be the same. Right? So we wish to use coordinate system, but what we're really interested in is the invariance. Right? Things like distance, angle, or in Euclidean geometry, and also curvature down the road. Of course, that's a much more complicated notion. So what we do is we choose a middle ground. Okay, we choose a middle ground. So the component of, say, a vector is different under different coordinate system. That's certainly true. However, because of the fact that the vector itself is invariant, the coordinate representation of vector components in different coordinate systems should not be totally random. Right? They should conform to certain laws to represent the same object. And that's exactly the underlying idea of tensors. So here, in the second stream, we considered the tangent vector of a curve. I consider the tangent vector of a curve in an n-dimensional space, and you can think of that as a three-dimensional space, a tangent vector in a curve. And how do the components of the tangent vector transform under coordinate transformation? You can easily derive that using the chain rule, which turns out to be a special case, of a tensor. So this is the idea of a tensor. So tensor is about studying invariance. Right? It's really about studying invariance. So the collection of the collection of numbers, right, organized in this multi-index array is called a tensor if it satisfies this transformation law. All right, and of course, this still aesthetically looks kind of horrible, if I do say so. That, right? I mean, it's a brilliant idea, but there are a lot of opponents of this definition, especially nowadays, because this looks horrible. Is there a better way to package this, right? Is there a better way to package this? It turns out there is, which brings us to our third stream on tensor analysis. And that video, the name of that stream is called Tensor Analysis, Modern versus Classical. So what we've seen earlier, all classical tensor analysis. The modern version of tensor, the definition is surprisingly simple. The definition is surprisingly simple, and it's what we call a multilinear form. It's a multilinear form. So suppose you have a vector space. There's a vector space, say V. T is a tensor. If T is a multilinear form, that is to say, T have multiple arguments, okay, let's say k arguments in total, it is linear in each argument, meaning if you keep all the arguments fixed except one, and t is a linear function in that argument. So that's the definition of tensor. Right? So mathematically, this is more elegant, right, compared to the horrendous transformation formula we've seen earlier. However, nothing new is introduced. Nothing new is introduced. It's just a quote-unquote coordinate-free notation that modern mathematics tend to prefer. However, that does not diminish the usage and power of index notation, because when it comes to actual calculation, you still need to work with, well, coordinates. Right? So this definition is helpful conceptually. So what we did in the last stream, in the third stream on the 25th, is that starting from the modern definition, you can derive the transformation law. For example, here you have earlier we have the contravariant transformation law. You got the covariant transformation law, and that's just for 1D, rank 1 tensors, and you can do that for rank 2 tensors, and the basic idea extends to any order. So far, right now, there shouldn't be any doubt that you're still dealing with fundamentally the same object. Okay, it's the same object. There's no new math being introduced. It's just that different perspective of the same thing. Okay, so and from now we're going to stick to the index version, because index helps us with calculations, and at least at the very beginning. It doesn't matter what you study. I mean, it doesn't matter, unless you're studying differential geometry for its own sake. If you're using geometry for a particular end, chances are you'll be working with coordinates. So index notation, learning index notation is never a waste of time. Okay, so hopefully the logic, the objective is now clarified. All right, so last time we introduced definition of tensor, as mentioned, and you can define algebraic calculation. Okay, algebraic operations. Operations. My goodness, can't speak. Operations between tensors. For example, you can add two tensors and still get a tensor. And to do that, you need the tensors to be the same kind. Okay, you need the tensors to have the same rank. For the covariant, just basically the same number of covariant indices and the same number of contravariant indices, and they also have the same weight factor, which does not really matter that much now. Okay, perhaps it will come up useful later, but right now what matters is two tensors need to be compatible to be added. This is obviously expected, right? It's just like in linear algebra. If you can only add vectors to vectors, you can't add vector to matrices, right? If the number of indices don't even match, then addition is meaningless. Okay, and then we got this definition of a product of two tensors, and actually this is basically the tensor product. Okay, you might have heard this fancy word called the tensor product elsewhere. Once again, we're defining this in a very concrete manner. Now, the definition of tensor product, in its concrete definition, is extremely simple. So you just literally multiply their components as real numbers. Okay, you don't need. It's not unlike matrix multiplication. You need a separate formula. Okay, that's a new operation. For tensor product, you just literally multiply the components. What do we mean? So let's say, suppose you have a rank 2 tensor TAB. A upstairs, B downstairs. Okay, upstairs is the so-called contravariant index, and B, the lower index, is the covariant index. And if you multiply that, okay, if you multiply that with another tensor, so S is a purely contravariant. It only has an upper index. It's a purely contravariant tensor. What do you get? Well, you get a tensor of order 3. 2 upper index with 1 lower index. And what are the new entries? Literally the product. So, quite nice. Okay. So anyway, sorry, I was saying Chinese. Sorry, my bad. This is the next operation called contraction. So what do we mean by contraction? So contraction is this operation. So let's suppose you have multiple indices, first of all, in the same index. And you also need to have a mixed type. So it must be one up and one down. At least one up and at least one down. Okay, so purely contravariant or purely covariant tensors do not have this operation. It has to be only work for mixed type. So if you set, say, one of the upper index to be a lower index, or actually just if you set a pair of upper index and lower index, actually I just prefer the term upper and lower index, because whenever I use the term covariant and contravariant, I have to think of which is which. Okay, so this is what is immediately clear: upper index and lower index. So if you select a pair of upper and lower indices to be the same, then by the summation convention, a summation is implied. If the summation is implied, and if you work out the detail, you still get another tensor. For example, here you have three indices, and if we set I and k to be the same, this way I and k, due to the summation convention, are no longer free indices. So the only remaining free index is j. You got a j downstairs, and what's a downstairs? What's a downstairs index? That's a covariant index. So the resulting object after quote-unquote contraction is a new tensor. With only one free index downstairs. That's a component of a covariant vector. All right. So to summarize, tensor plus tensor is a tensor, provided they are compatible. A tensor times another tensor, and really they don't have to be the same kind. Okay? They don't have to be the same kind. Two arbitrary tensor being multiplied, you still get a new tensor. Okay, so it's like you can create higher order tensors by the product. In fact, that's typically how higher order tensors are constructed, using tensor product. Okay, and now you have an operation that reduces the order, namely contraction, appropriately named. Okay, so that's what we've been dealing with so far. There's a contraction. There's that, and also there's this quotient law. So I mean, we'll revisit these when we actually need them. So basically, what we did is a bunch of operations. We introduced a bunch of operations, algebraic operations among tensors. So I think now we are in a position to proceed with the new material. Okay, so they were like reviews. Don't worry, this is going to last 4 hours, if not more. So the 20-minute review is nothing in comparison. All right, starting with more examples. Examples of tensor operations. Okay. Tensor operations, examples. And by the way, the book I'm following is in the description. Hi, Marco. Good to see you again. You've been following the tensor series quite closely. Thank you very much. So we're dealing examples of tensor operations. Here we go. So this is example. How many? What's our labeling system? We didn't do any example. Couldn't watch that, and that's okay. That's okay. So remember, Marco, if you're new, if you just hop into the stream, basically last stream we did a sort of a digression, because I felt like there's a need to reconcile the classic definition and the modern definition. So you can watch that separately, and you can pick up what we're going to do now purely from the definition of tensor, which you've seen. I remember you were in chat when we introduced this. All right, so here, example. So let's revisit the Kronecker delta. This motivates me to return a differential I try to learn it once to give up. That's awesome. That's really awesome. Hopefully, this little exposition of what we did and for what is motivating, right? Because after all, I don't want any of you to treat me as a source of information. Like, treat me as a source of, no, that's never the purpose. Because first of all, I'm not qualified to do so on the subject. As I mentioned, like this, I did this like 10 years ago, and my knowledge has not been, well, in a very great state because of lack of practice. I'm just trying to justify everything I did so you can follow roughly the same path and perhaps even better and do so yourself. Okay, so anyway, we're doing examples right now. So remember, we introduced the Kronecker delta symbol, delta ij. Is delta ij a tensor? Is delta ij a tensor? Because right now we have a formal definition of tensor, don't we? And you can't just call everything with multiple index a tensor, just like you can't call everything with a single index components of vectors. If you take a linear algebra, vectors needs to satisfy the law of vector algebra. A classic example I use all the time is that 3D rotations on 3D rotations on vectors. 3D rotations cannot be represented by vectors, even though it seems intuitive that once you have a rotation axis, which is a direction, and an angle, which is a size, you can represent rotation as a vector. It doesn't work that way. Okay, that's an extremely superficial similarity. Okay, vectors need to satisfy the law of vector algebra, and tensors need to satisfy the law of tensor transformation. Not just because it has a bunch of indices, it's automatically tensor. And I was thinking of taking on my double degree in math. Now you made me sure to do this in the semester. I can't believe my vacations. Be able to watch the valuable content you called me. Okay, great. Should we test it? Exactly. Of course, that's exactly what we're gonna do. So. Actually, let me check. I was gonna label the examples with numbers. So here, last time we didn't do much example, but what's example number? Perhaps 12. Sorry about that. No, that's measure theory. That's a different one. Example 6 all the way here. Example 10. Do we have example 11? Let me see. Let me see if I have example 11. Actually, we do. We did one example in the second day, so let me just want to make sure we label that. Oh, actually here. Was it here? Or was it here? Yeah, this is example 11. Example 11. Marco was there. I remember this. This caused a little bit of a confusion, remember? So right now we're at example 12. Okay. Example 12 is the Kronecker delta is a tensor. Now it is a bona fide tensor. And we're going to verify the transformation law. It is a tensor. Because you can only absorb these definitions by working with concrete examples. So let's do that. All right. So anyway, here you got one upper index and one lower index, so it probably suggests that this is a mixed type tensor. Right? So why don't we check the mixed type transformation law to see if everything still holds up, right? So this is just following the definition. So you need to check. What do we need to check? We need to check that delta bar beta alpha, that's the new component, right? Delta bar alpha beta, this equals what? This equals delta ij. Okay, let's try not to look at the definition, but instead just write it down ourselves. Okay, so this is the left hand side. You got new components because it's a bar component. That's new, right? That's new. So, all right. So beta should be free. Beta should be free. On the right, you got ij on top and bottom. Okay, so I should be summed over, and j, and so must j be. But multiply with what? But let's not worry about the indices now, because that's a distraction. What matters is on the right, okay, on the left, you got new. These are new components. This is what matters, because it's okay if you don't write everything linearly from left to right. So this is how we can construct this sort of tensor transformation law from our mind without doing mechanical memorization. Okay, so you need to memorize certain more fundamental things, but imagine if you have to memorize a big formula and then reduce that to special cases every time. So that's a horrendous experience. So on the left, you always have the new component. On the right, you got the old components times some Jacobian. And speaking of which, what should the Jacobian look like? Let's ignore the indices for now, okay? All right, so because it's a mixed type, so you should have one forward Jacobian and one backward Jacobian. Forward Jacobian in the sense that d new over d old. So d new over d old, that would be dx bar over dx. That's d new over d old. And then, because of one lower index, you need a backward Jacobian. So dx over dx bar. And now you need to supply the indices. Well, as I mentioned, the old indices, the indices for the old component needs to be summed over. So let's put it I on top and j at the bottom. They both need to be summed over, and they can only be summed over if they're repeated indices. So time to add I and j. Well, because I is upstairs, so I should be here or here. Think about where I should be. Think about where I should be. Any idea, Chan? Because I is a upper index, aka contravariant index. It should be paired with what? Forward or backward Jacobian? It should be paired with a forward Jacobian. This is a contravariant index. By definition, it gets paired with a forward Jacobian. So this is a forward Jacobian. New, d old versus d new. So I should be here, but downstairs. Therefore, this is I. All right, what about J? Well, J is a covariant index. Covariant quantity is transformed by the backward Jacobian. So this is not the other one, right? D old over D new. So J should appear up here. And now you only have two index to fill up, and that's for the summation. So that's not a free index. Actually, sorry. My goodness, I'm stupid. So those two should be free. Okay, we just handled the dummies. IJ and IJ are done. So beta is on top, just like on the left hand side, and alpha is at the bottom. So this fixes up everything. Okay, so you should be able to write this formula from scratch based on the thought process I just described. Okay, just take a little bit of practice. All right, so we need to verify these. So we need to put a question mark here. Like let's verify. Is that true? Well, let's start from the right hand side. Right hand side. So right hand side. Well, that's just a delta symbol, right? What happens when you have a delta symbol? You replace the indices. So yeah, basically that's what you do. Replace the indices. So it's like recall. For example, x alpha delta I alpha is just xi. You just swap the index of whatever that has alpha to be the new index in the Kronecker delta xi. But the equal indices. What do you mean equal? Yeah, so Um, so the idea is you would change that to, hold on a second, let me try to justify that. Yeah, because of the delta, okay, this delta can be interpreted as such. Okay, this delta can be interpreted as saying, okay, whenever you see an I, swap that to j. Or it can be interpreted as, if you see a j, swap that to I. I think both works. So let's take the first option. Okay, let's do it two ways. Okay, right hand side is method one. Method one. So let's first combine the two. Okay, let me highlight that. This is method one. So here you're just changing j to changing I to j. So this way you just get a what dx. Sorry, wrong color. Dx bar beta, that's unchanged, and then over dxj, like this. I'll read the chat later, okay? So I'm just finish method one, and then times what? Dxj over dx bar alpha. But what's that? What's that? Well, that's just you see, this is just the matrix multiplication of the forward Jacobian times the backward Jacobian, and this gives you delta back. This is just delta of beta over alpha. Just delta beta alpha. Actually, by the way, this equation was derived in the first stream. Okay, let me go back to the first stream. Hold on a second. I'll take a look at the 23rd, right? The 23rd. And we introduced the delta notation. Yeah, we said it very clearly. Yeah, this is just a pure notation. That's just Kronecker delta. You know, where did we introduce Jacobian? Jacobian is here. Yeah, Jacobian. This is the identity. Let me box that now. So first of all, delta ij can be expressed as dyi over dyj, because yi's are all independent variables. If you have the same index, you get 1. You have different indices, you get 0. And then you can use the chain rule. Treat x alpha as intermediate variable. Use the chain rule. So this is the equation we invoked. Okay. So what does this mean? Well, this is just as I mentioned, right? This is just the Kronecker delta beta alpha, but this is equal to delta bar. Is equal to delta bar beta alpha, because when does delta beta alpha equals 1? Alpha equals beta. When does it equal 0? When the indices don't match. And this is the same function or double sequence, whatever you want to call it, as delta beta alpha. So that's the left hand side. You're done. Okay. So yeah, and now we can try another method. So let's say combine delta ij with the last term. Okay, so this is method 2. This term with this term, this is method 2. So by method 2, what do we get? Well, delta ij still does the same thing. It either swaps I to j or swap j to I. In method 2, the second expression has a j, so it gets swapped to I. So dx bar beta over dxi, that's the middle expression, middle factor, which is unchanged. And now just change, and then just multiply by dxi over dx bar alpha. And of course, this is still delta beta alpha, because take a look at up and down. The only difference is the dummy index. So they're the same thing. So this is still delta bar beta alpha, which is the left-hand side. We're done. QED. So this finishes the proof that the Kronecker delta is a tensor. All right. So, sorry, Arad, I didn't have time to answer your question until now. Is there a reason that the denominator of the forward Jacobian is x? You mean the upper and lower index? Good question. Good question. So, for coordinates in tensor analysis, we always use upper index, because you can think of the reason why. The reason for that is I think it's explained in the last stream, the reconciliation between modern and classical notation. First of all, I mean, in a way that that up or down is arbitrary, but what? But if you make a choice about, say, the position of indices in one kind of object, say vectors in a vector space. So let's say for vectors in a vector space, if the basis vector uses lower index as by default, okay, then you have to accept its consequence. That's exactly what happened. So you can memorize the fact that the coordinate indices are upstairs. You can just use that. But if you want an explanation, we did so in our third stream. So starting from the usual linear algebra notation, if you write a basis of vector space using lower indices, then by the summation convention, this forces the coordinates to pick an upper index in order for the summation convention to work. Okay, so that's the idea. So if you, let's say, E1, E2 all the way to the end, this is the old basis vectors. Hopefully that's clear to everybody. And then if you expand an arbitrary vector in that basis, then the coordinate will pick up an upper index. So that's why we use the convention that coordinates are meant to, coordinates, you always, for coordinate component, you always use upper index. Okay, so hopefully that's clear. Okay, and every time we write something like this, okay, every time we write xi, x bar beta, whatnot, we always assume there's a coordinate transformation going on. Okay, from x1 all the way to xn gets transformed to x bar 1 all the way to x bar n. So this is implicit. Okay, bar is the new coordinates. Okay, unbarred is the old coordinates, because that's the example. All right, let's continue. Example 13. All right, example 13. So let's say if you got AI, right? Given AI, upper index, given AI and BI, I is lower. Of course, to review the terminology again, AI upper index is the component for contravariant vectors, and BI lower index is components for components for covariant vectors. Right. Given those two, you can define the new mixed tensor Cij. Cij as AI upper times Bj lower. Regarding the topic of indices, one use of the metric is lower and upper. We'll talk about metric stuff soon. Metric tensor. metric tensors for upper index juggling. In fact, for metric tensors, there's a covariant and contravariant version. All right, so yeah, so it's actually very consistent. The tensor index notation is very consistent. So here, let's define C to be this mixed tensor. All right, and actually, let's verify this is indeed a tensor. I mean, of course, this is a special example we had defined earlier. Right? We already showed that in general, tensor product gives you, well, another tensor. The product of two arbitrary tensors gives you another tensor. Let's just try to verify this is indeed another tensor. Right? Check Cij, because not everybody not everybody attended the last stream, right? So check this is indeed a mixed tensor 1, 1 of order 1, 1, mixed 1, 1 tensor. So let's do that. Well, since AI is upper, uses upper index, so how do AI transform? You get A, actually, let me, redo this business. So first, let's say, on the left, you just have A bar I, okay? We'll leave it now. And on the right, what should the overall structure look like? We'll ignore the index for now, okay? Just ignore the index. I think this is a good order to write things. On the left, you always have the new coordinate. I just call it A bar I, okay? I is a free index, just like in the expression AI. All right, so, well, how should A transform? Well, you got an A, old component. Something needs to be filled here. Okay, and then multiply by a Jacobian. So what's a Jacobian? What would be the appropriate Jacobian? Well, because this is upper index, so use forward Jacobian. Dx bar over dx. Once again, the indices are missing. Something is missing here, something is missing here. All right, so let's fill them up. All right, so on the left, I is a free index, which means on the right, I also should be a free index. And it's upper, so I should be here. And the rest of the two indices are summed over, so you can write A alpha and downstairs dx alpha here. So yeah, that's the first equation. Yeah, forward Jacobian, exactly, thank you. And B bar J should be what? This is the left-hand side. Okay, so let's follow our procedure of writing the transformation law. On the right, you have B. Don't write the index now. But because it's downstairs, right, so it should be d old over d new, dx over dx bar. X over dx bar, all right? So J is downstairs. So we put a J at the bottom of dx bar. So put a J here. All right? And the other two indices on the right, one for B and one for dx, should be the same. They need to be summed over. So let's say you write B beta times dx beta over dx bar J. All right? So this is a given quantity. So now let's define C. Well, now you have defined C. How would C transform? Let's check if C satisfies the transformation law. So let's just write C bar. All right, so C bar of what? C bar ij, let's say. This is C bar ij. C bar ij, by definition, the definition should be A bar I times B bar j. By definition. All right, but we have our formulas for A bar I and B bar j. You now just substitute, you get A alpha dx bar I over dx alpha. and then times b bar j. What's b bar j? That's b beta times dx beta over dx bar j. Okay, a quick sanity check. On the right, you should have two free indices I and j. And indeed, we do. Both alpha and beta are dummies. Okay, and now let's collect. Say, you put A alpha and B beta together, and the two Jacobians does not look like you can simplify, huh? Which is okay. What is A alpha B beta? That's just the C alpha beta. So indeed, the components of C satisfies the transformation law for mixed 1-1 type tensor. Mixed 1-1, right? For mixed 1-1 tensor, the transformation law should have two Jacobian, one forward, one backward. Hi, Alex. So yeah, so that's proved. This is indeed a tensor. Right? This is nothing but a special case of the proof we did last time on Saturday, that the product of any two tensors is a tensor. Same business. All right. So here we're just doing it for this special 1-1 tensor. All right. So that's example 13. Let's continue. And speaking of which, right? So Marco was asking about metric tensor, and that's exactly what we're doing now. So here, example. Here actually we get to see how the weight of the tensor can play a role here. So this is example 124. Okay. So here let's consider given Gij. Why it's called a metric tensor would be clear when you see some Riemann geometry, actually. Riemannian geometry. Hopefully we'll get there today. I think we will, actually. Today we'll define what is Riemann geometry, or Riemannian geometry, from a computational perspective. So here you have, this is a purely covariant tensor. I mean, at least the notation suggests so. Okay. Suppose you have Gij. Whenever you write this, okay, we assume it satisfies the transformation law. Actually, you know what? We can't really assume that. We have to be more verbal, because not always you have this. Because later on we encounter something called a Christoffel symbol. Later on, okay, just down the road, we'll encounter something called a Christoffel symbol, in which there are three indices. But it does not imply that it's a tensor of order 3. Okay, so here let's be more careful here. So here in the previous example, AI is taken as contravariant, and BI is covariant. Okay, and here Gij is purely covariant. Let's be explicit about those things. Okay. Okay, so this is Gij, and what do you have? There was an example we did in the first stream. We need to recall. Okay, so in 24th, actually 23rd. Example about determinant. Remember, determinant is multiplicative. So let's apply that to our analysis here. So Gij is purely contravariant, meaning G, let's write down the transformation law. Say you got G I bar J bar Okay, it equals what? So first of all, you got g and 2 backward Jacobian, dx over dx bar, dx over dx bar, and now add the indices. Okay, because you got 2 ij's downstairs, so 1 I here, 1 j here. And on the right, let's just say g alpha beta, 1 alpha up, 1 beta up. So that's the transformation law for g, right? And now let's think about and now let's just treat all of them as matrices. Right? We know, right? We can treat them as all matrices and take their determinant, because determinant is defined for all, well, for all matrices, or more generally for all double indexed arrays. Right? If you have a double indexed array, it does not matter where the indices are, upper or lower, it does not matter. You can still apply the determinant formula. Right? So every term involved here has 2 indices, which means you can calculate determinants. And it still makes sense. So you can take the determinant on both sides, take determinant and use the multiplicative rule for determinant. The multiplicative rule is example 5. Here, see that again. Okay, determinant, and this law for determinant, even though here we use 1 upper and 1 lower index, you can show this is still true if you both have lower index and you have both upper index. Right, this is, you can prove that, but it is clear from just basic linear algebra. If you have a double index array, you can define determinant, and the property of determinant does not depend on the location of the indices. So, taking determinant, on the left you get g bar determinant, which we just write g bar in this notation, g bar absolute value. Okay, this just means the determinant of this 2 double indexed array, which equals g determinant, okay, and then times the backward Jacobian determinant squared, because these are the same matrices, and you should get the same determinant and then square. Sorry guys, I just need to use the bathroom in a sec, and I'll do that real quick. Sorry. I'll be back. Okay, in like 3 minutes maximum. Hey guys, yeah, um, yeah, I haven't finished talking, so because I just gotta use the bathroom. Okay, sorry, my bad. So yeah, I mean, I haven't finished writing this example, so it's perfectly justified that you don't know where we're going. I'm just saying that in the transformation law, you have in total of four double indexed arrays, and the function determinant does not care about the location of indices, even though we proved the properties of a determinant for a mixed type tensor notation. Okay, but determinant is defined for any double indexed array, just like in regular linear algebra. In linear algebra, you didn't care about the location of the indices. You can use upper, lower, whatever, and the determinant is still the same, and the properties still hold. Right? So if you write this as a matrix multiplication, this would be the G bar matrix equals the G matrix times the Jacobian matrix squared. And apply determinant or take determinant on both sides, you get this equation. All right. So, and this is of course the same as the square root. Okay. I mean, by taking the square root, we're assuming that the determinant is positive. Okay, just for the sake of argument, let's just be able to, just for the sake of proceeding this further, we're not introducing complex number or anything. Okay, assume G has positive determinant. Okay, G has assuming this has G has non-negative. G has non-negative determinant. Then you have the square root of G bar determinant equals the square root of G determinant times should probably use the absolute value sign, but there's already a bar here, which is kind of annoying. Okay, for that reason, let's also assume the Jacobian determinant is positive. It cannot be just greater or equal to 0. If it equals 0, then it may not be the coordinate transformation may not be invertible, which is bad. So assume this is positive. Okay, so assume the backward Jacobian determinant is also positive. Then you have this equation. Okay. So, and now what? So let's think about the consider. And now let's consider. Let's start here. Too many empty spaces. Why do I do that? Now consider AI as so-called absolute. So an absolute contravariant vector. So AI satisfies AI bar equals A alpha times dx bar I. Remember, in the tensor definition, whenever there is no determined factor at the front, we call it absolute tensor. So actually, earlier we all considered absolute tensor. So without by default, okay, tensors are all absolute by default. If you don't say this is an absolute tensor, it means an absolute tensor. So AI satisfies this. This is absolute contravariant. Let me finish writing that. Okay. We will show that. We'll show a new quantity which is b bar. Let's consider that as b. Let's show b bar, not b bar, but bi defined as the square root of G determinant times AI. show this thing as the as is contravariant with what is it called last time? Terminology here. Actually, in 24th. Okay, so this is where we define tensors with density. Yeah, I want to show that n is equal 1 for B. Okay, let's show that. Okay, so show this new thing is contravariant with density. Contravariant vector with density. Okay, and just for convenience, I'm gonna copy paste the everything here to the right of the example, because let's be honest, this is not the easiest definition to memorize. So this is what we mean, okay? Even though I'm going to shrink things down a little bit. Yeah, just to recall definitions. Okay, so let's do the proof. It's not very long, but once again, you just try to derive the transformation law of BI. So what's B bar I? Well, so by by the definition of B bar I, this is just the square root of G. Remember, this is just a number. Square root of G determinant is just a number times A bar I. And then substitute the transformation law for A. You get the square root of G determinant, and you get A alpha dx bar I over dx alpha. Dx bar I over dx alpha. Oh, sorry, my bad. G bar should also be used here. I mean, this is not a scalar. A scalar, okay? The scalar is something that doesn't change whenever a coordinate is changed. Okay, so this is something perhaps a little bit easy to make mistake. In tensor analysis, the word scalar takes on a different meaning. Okay, or shouldn't say different, but basically specific meaning. A scalar isn't just a number. After all, components of tensors are also numbers. You don't want to call that a scalar, do you? A scalar is what we call a rank 0 tensor. And its transformation law is very simple. It doesn't change. A scalar is a number that is invariant under coordinate transformation. And that's what we call a scalar. Here, G, even though it is a G determinant, okay, even though it is a number, it is not a scalar because it changes according to this factor, given a coordinate change, right? It makes sense. So think of linear algebra, let's say you calculate the determinant of a matrix, and the matrix is the representation of a linear operator. Right? And actually, linear operator shouldn't, my bad, I mean, linear operator, the determinant of linear operator is an invariant, actually. Here, this is, okay, this is not a linear operator, because the linear operator needs one upstairs, one downstairs index. Anyway, that's a bad analogy, my bad, okay? So, yeah, but basically, you can just stare from look at the equation, and you can tell that under coordinate transformation, the determinant of G changes according to this law. So it's not invariant. Okay, so here, that's why we should put a bar here. I missed that. What changes the values of the determinant itself and not the fact it's zero rank tensor? No. zero rank tensor literally don't change. Zero rank tensor literally don't change when it comes to coordinate transformation. Let's think about, let's take a look at an example, okay? It was shown last time. Right, so let's say you have A alpha and B beta. Let's consider this expression here. Sorry, AI and BJ, AI and BI are components of a covariant and covariant and contravariant. Sorry, AI is contravariant and BI is covariant. And you consider this quantity, A alpha, B alpha, one up, one down. Okay, you consider that, and you can show this is a scalar by checking that it remains invariant. It remains an invariant under coordinate transformation. And here's a quick proof. Right, here you have the coordinate transformation law for A and B, and you do this calculation, and it turns out that A alpha, B alpha is the same as A bar alpha and B bar alpha. So yeah, this is a rank 0 tensor. The product is called a scalar, or dot product, or whatever. It's called a scalar. Okay, so scalar in tensor analysis takes on a very specific meaning. It is a number. It doesn't matter how you use the coordinate system, it's the same value. If that makes sense. So here, based on this formula, you can already see that G determinant is a number, of course. That's trivial, but it's not a tensor. It's not a tensor, so a scalar, a number that is not a rank 0 tensor is not a scalar here. A scalar in tensor analysis takes on a very specific meaning. It's literally just T bar equals T. No Jacobian, none of those fancy stuff. Okay, it's literally just, as you can see from the example, if let's say if T, no index, is a scalar, it means T bar equals T. An invariant in itself. Because remember, you don't need components, you don't need extra components to describe a scalar, do you? You just need one number. So, as we mentioned earlier, tensors are meant to describe invariants. For a vector, a geometric invariant, in itself, the geometric object stays constant, but the component changes. But the component changes once you switch coordinates. Scalar literally don't change. Here, G determinant is not a scalar because it changes. You see, G determinant changes when you use different coordinate. Okay, so hopefully that's cleared up, because the fundamental issues are easily confused in the early stage. All right, so yeah, so this is B bar I. B bar I should use G bar determinant square root times A bar I. Okay, and we just write down the transformation law for A bar I. This is the transformation law for A bar I. But what about square root of a determinant of G bar? Well, we have that here. You need to pick up another Jacobian. You need to pick up a Jacobian like here. Okay. This is A bar I. We know that. And this is a forward part. Okay. And now we see you can combine square root of G determinant and A alpha, and that's just B alpha. So this is dx over dx bar determinant and then B alpha. This is B alpha here, B alpha. And then dx bar I over dx alpha. So take a look at the the result with the definition. So big N equals 1 here. Big N dx over dx bar determinant has a power of 1 here. And on the right, you got the usual rule that we're familiar with. So according to this definition, it says if big N equals 0, we say that the tensor field is absolute. Otherwise, the tensor field is relative. Otherwise, the tensor field is relative of weight n. A tensor density occurs for n equals 1. So here a density occurs because big N equals 1. And because the tensor itself only uses one index, we call that a vector density. So we call this so therefore Bi are components of a contravariant vector density. Okay, so finally we have seen an example of a non-absolute tensor because of this factor. Previously we never dealt with that in actual examples. Okay, here we're seeing an example of a non-absolute tensor. Okay, so hopefully this is clear. Okay. All right. So now let's keep looking at this quantity, say Gij or G alpha beta. Okay, let's assume this defines an invariant. Let's assume this defines an invariant. And here's the motivation. Let me just put it on the side. Okay. Let me first write down the premise of the next example. So example 15. This is example 14. Okay, example 15. So assume you got an invariant. G alpha beta dx alpha dx beta is invariant. Okay, what do we mean by that? We mean G alpha beta bar dx alpha dx beta, okay, equals G alpha beta dx alpha dx beta. So actually we're going to give two motivations for this because this is really the idea of a metric tensor. So this is about measuring distances on manifold. This is about measuring distance. So for the physicists in chat, you might have heard about special relativity. In special relativity, there's something called the Minkowski distance or Minkowski metric. Basically, for example, in special relativity, let me just answer Marco's question first. In the definition of a tensor, the term with the tensor density is written in backward Jacobian. Would I change if the forward Jacobian here? I never seen an example of forward Jacobian actually. I never seen a forward Jacobian. Perhaps that will simply never arise. Once again, I don't know. Like because if this is a general definition of tensor, perhaps you will never see on the right hand side dx bar over dx absolute value determinant. Perhaps you'll never see that. Perhaps you always use backward Jacobian for the determinant. You know what I mean? Perhaps you always use the backward Jacobian for the determinant. Because so far we've never seen any situation that indicates otherwise. Of course, forward and backward Jacobian themselves can appear on the right. Maybe there's a reason. Maybe. Yeah, I can't say that for sure. Okay, I can't say that for sure. Or just the way the formula is made. Perhaps I can give a plausible explanation. Okay, perhaps I can give a plausible explanation. So let's consider, say, the change of variable formula from calculus. Say, change of variable formula from calculus. Let's think about the classic example from Cartesian to polar. I gave that example on 24 stream, didn't we? Didn't we? When I attempted to explain this mysterious looking factor here, I used the polar and Cartesian transformation example. Right. So what do we mean by that? So it's, think about the integral of f of x dx dy, right, over the region, say rxy, and let's say you have the coordinate transformation from xy to r theta, right, from Cartesian to polar. And what would be the change of variable formula on the right? Well, that would be f of x of r theta, y of r theta, right, and then times the Jacobian. So first of all, on the right, you should have dr d theta, and the Jacobian would be d of x and y over d of r and theta. You see, this is the backward Jacobian. This is backward because you got d, see, d old over d new here over the region r theta. So I can hardly imagine a situation where you have a forward Jacobian appear here. So it's like dxy equals this. Remember, dxy is supposed to represent the area element, right? Area should be an invariant, a geometric invariant. It should not depend on how you parameterize it or you use coordinate indeed, right? So basically, this is perhaps the reason why you never see a forward Jacobian on the right. The transformation formula simply do not require that. Okay, but anyway, that's the idea here. So anyway, let's come back to the example here. So before we proceed, let me just try to give a little bit of a explanation for this. So for example, in special relativity, you can show that x squared plus y squared minus x squared plus y squared plus z squared minus c squared t squared, see, where c is the speed of light. This is invariant under the so-called Lorentz transform. Is invariant under the Lorentz transform. Okay, so and also if you don't know special relativity, but just going back to regular Euclidean geometry, think about how do you calculate arc length on the surface? How do you calculate a small arc length on the surface? So this is a line element. It's called line element on the line. Line element on the surface. Think about measuring the distances between two close points on a curved surface, like the distance from, say, New York to Washington. Right? On a global scale, the two cities are quite close. And the distance between them, is called, actually the distance squared between them is called a line element. So let's think about the situation here. So imagine you have a curved surface, line element on surfaces. All right, so this is a surface. And like in regular calculus, we often parameterize a surface using, well, parameterization. So how do you do that? Well, you do a parameterization in this form. So r of position vector r as a function of two parameters, say r as a function of uh, of x of u1 of, let's say, uv. This is a parameterization. The surface is this. Okay, this is the surface, or at least a small patch of the surface can be represented this way. And if, let's say, if u equals constant represents these lines here, these lines on the curve, so these are constant u, and also you can have constant v. You don't have to be orthogonal, but they cannot be tangent at any point. They have to intersect at a non-zero angle. Okay, so this is constant v. The constant v. So the question is, how do you say calculate the distance on the surface? Right? How do you calculate the distance on the surface? So imagine a creature lives on the surface. It doesn't know the ambient R3. Its sense of distance is governed by the surface R of uv. So, well, we know that you can write the length element ds squared in the Euclidean way, which is dx squared plus dy squared plus dz squared. Actually, that's inefficient. You can just write ds squared as dr dot with dr, right? That would be a perfectly valid definition. dr dot with dr. But what is dr? dr, the total differential by the chain rule, is partial derivative. Okay, partial derivative, the dr over du times du plus dr over dv times dv. And then by taking the dot product, you just get this. Taking the dot product, you just get the dr over dv, right, dr over du norm squared. Actually, let's just write dr over du, dr over du, du squared. All right, and then plus dr over dv dot with dr over du dot with dr over dv, the cross term, and then du dv. And finally, you got dr dv dot with dr dv dv squared. dv squared. As you can see, this is a double summation. This is a double summation, and that's basically what we have here. So you can define GUV to be this matrix. Okay, GUV to be this actually just G matrix to be dr du dot with dr du, dr dv, dr du dot with dr dv, here dr dv dot with dr du, and lastly dr dv. Right? So that's the matrix here. And therefore you just get ds squared equals GUV du dv with a summation notation. U and v are both summed over. Actually, you know what? Just to emphasize that, let's use a double summation symbol. So that's the motivation here. So as you can see, why this is called a metric. Okay, so of course, in Euclidean geometry, the line elements on the surface just infinitesimal length squared on the surface, it shouldn't be dependent on the parameterization, aka the coordinate system. So it's natural to assume that the resulting ds squared is invariant. So assume this is an invariant. So this seems like a reasonable definition now. Okay, we would like to show that this has to be symmetric. Hang on. This has to be. No, it doesn't have to be. It doesn't. Okay. We assume that it is symmetric. So we assume this is symmetric. So assume. I mean, here as you can see, we assume. We didn't assume G is symmetric. Its symmetry comes from the symmetry of the dot product. So this is really just a generalization of what we did, this matrix here. So we can assume that G is symmetric. Actually, we'll assume that at a later point. Okay, just right now, we'll be using this assumption later, so why don't we put that later? Assume G alpha beta equals G beta alpha. What's so nice about this is that once you have this formula, and if you have, let's say, a symmetric matrix G, then you can just work with G and forget about the parameterization itself, right? So here, the G is derived from a particular parameterization. And by the way, dr over du has a meaning here. What is dr over du? Well, dr over du is just the tangent vector of the surface along constant v. Remember, the definition of a partial derivative is about controlling variables. When you say partial derivative dr over du, you're treating v as constant. So that's just the tangent vector of constant v curves. So this vector here is a constant v curve. This vector is dr over du. This is dr over du, right? And then the second vector, dr over dv, of course, that's the tangent vector of constant u curve. Like here, like this. So this is dr over dv. So this is dr over dv. So in this little example, we started from the parameterization of the surface with two coordinates u and v, or two parameters u and v. You can immediately derive, well, dr, that's like an infinitesimal displacement, right? Imagine the gap between these two constant v curves is dv. The gap here is dv, and the gap between constant u curve is du. And this is a linear combination. dr can be seen as an infinitesimal linear combination between the two tangent vector. So this is like the dr. And then dr squared is just the length of that infinitesimal vector squared. Square length of that infinitesimal vector. So you started from the parameterization, define the tangent vectors, and then calculate this G matrix to get the distance square formula. Right. However, if you just are given the G right from the start, you can skip the previous definition. You can skip the previous derivation. I just work with this as a geometric quantity on its own. And geometric quantity meaning invariance on its own. Right. So that's the idea here. Right. And it is not so difficult to imagine. We can assume G is symmetric, just like here. It's a generalization. This is example 15 is a generalization of what we've done over here. Okay, so there's that. Assuming this is an invariant, let's see what we can accomplish here. What are the consequences of that? Well, I forgot the bar, my bad. Because dx bar, dx bar, so from dx bar, what is dx bar? Well, dx bar alpha is partial x bar alpha over dx mu, and then no partial, just little d x nu. Right? This is just a chain rule. Right? This is just the chain rule or the formula for the total differential. Did we write that down in the first stream? I think we did while giving examples of the summation notation, didn't we? Yeah, we did. This is the formula for the total differential. Right? So the idea is, in general, if you have a function f depend on n variables, its differential, total differential, df, is this thing. It's just a chain rule. Here, and we're using that for x bar alpha. So dx bar alpha, the differential, dx bar alpha is this thing. And of course, you have the same business for dx bar beta. It's just a change of notation. You can write partial dx beta over dx without the bar, call it nu, yeah, and then d of x nu. Right. So substitute those in there. To the left hand side, we got g bar alpha beta times dx bar, which is partial x alpha over dx mu, and then times dx bar beta over dx nu, and then the differential dx mu times dx nu. Okay, that's the left hand side, and is equal to the right hand side, which is this is g alpha beta. Why don't we change that to g mu nu? Okay, because we want to compare how the g behaves under coordinate transformation. So let's make the dummy indices the same. So on the right, you can write it as g mu nu dx mu dx nu. All right. So, hold on. Yeah. If we assume this, if we assume G is symmetric, what happened? If we assume G is symmetric, then based on the definition, hold on. We wanted the goal is right in our face. We want to conclude that the two are equal, right? So this is the transformation law for G that we wanted, but still, we're trying to see why that's the case. How can you justify this sort of cancellation, basically? We have, hang on. I think earlier we justified that perhaps in the first one, example 4 maybe. Yeah, here in example 4 we said, remember this example, it says S equals A alpha beta, X alpha X beta equals 0 identically. If this equals identically, then the hold on a second, then you must have, if this is the case, then you have, if it's identically 0, yeah, if it's identically 0, then you must have symmetric indices, actually anti-symmetric indices. And here's a quick proof, okay? This just means that the diagonal elements are 0, and what's that? And the off-diagonal elements are
anti-symmetric. If you exchange the order of diagonal elements, you pick up the minus sign. Right, so there's that. Let me put that down over there. So we're going to use that. Good exercise, by the way. So this was the example from the first stream. Let me change that to a different color. We're using this result here. All right, so at this point we wanted to just do some rearrangement. All right, so you got g bar alpha beta dx alpha d bar of x alpha over dx mu times dx bar beta over dx nu minus g mu nu times dx mu dx nu equals 0. And this equals 0 identically. So we can use this theorem. Okay, so we can use the theorem from this theorem, from this example. By this example, then this big index should be anti-symmetric. Sorry, this big coefficient must be anti-symmetric. Recall from this example that this got to be anti-symmetric. All right, so it's going to be anti-symmetric. Hold on a second. It's identically 0. If we assume this is so, therefore, let me write down the consequence here. So you should have g bar a alpha beta downstairs dx. The reason we can't just declare this to be 0 is because this is not a straightforward cancellation, because you have to sum over I forgot equals 0, by the way. You can't just say, oh, because of cancellation this is 0. I'm a applied mathematician and data scientist in the retail sector. Right now I'm on vacation, so I'm able to stream more. So I was saying that if this is 0 identically, then this big coefficient should be anti-symmetric from our example 4. So let's write down what that means. So this is because alpha and beta are the dummy indices, so they don't matter. You just need to change the order of mu nu. Here, remember, here this is a double index with index mu nu. So dx bar alpha over dx nu, not mu anymore. Okay, I'm changing the order. And then dx bar beta over dx mu minus g mu nu minus g mu nu equals what? Equals the negative of this thing. Equals the negative of this thing. So it's minus, let me just copy that. It's a lot of writing. Minus sign here, plus sign here. Plus sign here, okay. And So what we got here? I guess now we can use the fact that this is a symmetric this is a symmetric quantity. G alpha beta equals G beta alpha. And then what? Oh, sorry. Here I messed up. No wonder. Here I messed up. It should be G nu mu. G nu mu. The purpose of this example is to show that, okay, we would try to show that from these two assumptions. Let me just highlight that. Assuming this is invariant and G is symmetric, G should behave like a tensor. That's where the name metric tensor comes from. By that we mean if these two hold, then eventually we want, okay, G mu nu equals G bar alpha beta times d bar alpha over dx mu, and then times dx bar beta over dx nu. So there's that. So we want that. We want that to hold, but what is the final step here? Here we assume symmetry. Here we assume symmetry. So, well, so I guess you can write this as, I mean, if this is symmetric, we can't actually, can we just say, if this is symmetric, then, oh, actually G alpha beta here is also the same. I guess you can factor them out. Let's just do the rearrangement. Hopefully this is easier than imagined. So this is just G bar alpha beta times the product of those two. Okay, and then plus this thing, plus this thing. All right, and it equals to 2 times G mu nu, equals 2 times G mu nu. All right, because since we have G mu nu equals G nu mu equals G mu nu, right? These two are the same. So this is after rearrangement. But here, what can we say about that? Are those two the same? Serious question. Are those two the same though? Yeah, the two are the same. It's just the two are really just the same. So you can see this is just exchange the order of the two. So it's literally just 2 times dx alpha over dx nu times okay, bar on top, I missed that, dx bar beta over dx mu. Okay, then 2 cancels. We finally got our answer. So the moral of the story is, assuming the 2, we show that G is i.e. G is a tensor. It's a purely contravariant. It's a 0-2 tensor. So a purely covariant tensor, sorry, of rank 2. That's the conclusion here, called the metric tensor. Okay, and this is actually the fundamental quantity in Riemann geometry, Riemannian geometry. Okay, you have the metric tensor, just like in inner product spaces. So, in inner product spaces, linear algebra, we can do geometry. You can calculate distance. You can talk about orthogonality, calculate angles, that sort of thing. In Riemannian geometry, the metric tensor plays a similar role. So in a Riemannian geometry, you have a curved surface just like this one, although it's usually quite abstract. It might not be a subset of R3 or Rn in general. But you still have this G over the manifold, so you can do things like calculating distances, angles, and whatnot on the manifold using this G. So what we managed to show that is if you have an invariant associated with the G, so basically this is a quadratic form. If G is a quadratic form that's invariant, okay, and in the double index array, the components are symmetric. And if you assume the components are symmetric, then it is a 0-2 tensor. Okay, so that's cool. That's cool. So it's covariant tensor of rank 2. Okay, and now let's more example. Okay, so this is a lot of example, which is necessary because you really eventually you wanted to achieve fluency when it comes to index notation and tensor definition. That it just like autopilot. Okay, you just do these index contractions and without thinking much about them. And of course, occasionally you do need sanity check, but the idea is this should be running on autopilot when you do actual geometry. So that's the idea here. So the next example, which is example 16, says the following. So if the components of a tensor are 0 in one coordinate system, right, then are identically 0, okay? If the components are all identically 0, then it should be all identically 0 in another coordinate system. Right? So this is a trivial result, obviously. Right? If t is identically 0, then remember, the t on the right is not just one term, okay? It's a sum. So this really means for all the indices, t is identically 0. If that's the case, then the new components are all identically 0 as well. I mean, it's a trivial result, but it is said that this will be useful, very useful later. So let me just write down um, the, uh, the verbal description. If components of a tensor equals 0 in one coordinate system, because I mean, it's not a linear transformation, but yeah. The component of tensor is 0 in one coordinate system, then the the components are 0 in all coordinate systems. Okay, so that's example 16. And um, example 18, example 17, example 17 would be the outer product, so-called outer product, also known as Kronecker product. Okay, so outer product of two vectors. So this is defined as such. So let AI be a covariant. As you can imagine, Cij is covariant. Cij defined as AI times Bj is covariant. AI downstairs, Bj downstairs is covariant. And the proof is very simple. You just substitute the law of how AI and Bj transform. So say Cij bar by definition is AI bar Bj bar. Use the transformation law. So A times dx bar over, actually dx on top, dx bar on at the bottom, and then B times dx over dx bar again. Okay, now time to add the indices. I here, actually no, I here, alpha, alpha, beta, beta. Okay, that's cool. So A alpha times A beta, of course, that's just C alpha beta, both downstairs. All right, and then dx alpha over dx bar I times dx beta over dxj dx bar j, right? So that's it. Proof. Okay, done. Okay, so um, hang on. Cool. May I just completed a linear algebra lecture about orthogonal projection. Sorry to interrupt. Sorry, I forgot to answer a question. Marco was saying, so for G to be a tensor, it needs to be associated with quadratic form and have the property of symmetry. Yes. Yes. You're totally right. Yeah, totally right. It needs to be invariant. It needs to be from the assumption that the quadratic form is an invariant, meaning doesn't change under coordinate transformation, and the assumption that G alpha beta is symmetric, then you can deduce the tensor property. I think it is a common mistake. It is a common mistake to go from here and immediately conclude, oh, the two must be the same. As if dx mu and dx mu and dx nu can be cancelled. Remember, this doesn't work that way because this is just one equation, right? This is just one equation, and there's a summation being implied. You can't just cancel them out. There's no such rule for you to do so. However, we do know if you, let's say, I mean, from this point, you do have, okay, you do have the difference is anti-symmetric. I guess you can say because we have symmetry, and you have the difference is anti-symmetric. Right? This difference here is anti-symmetric. It has to be zero. It's symmetric and anti-symmetric at the same time. So it has to be zero. And so therefore, the tensor transformation law is obtained. So somebody said, "Ah, man, just completed a linear algebra lecture about orthogonal projections." Sorry to interrupt. No, you're not interrupting. Interesting stuff. I need to catch up from the start. Yes, I think that would be very necessary because we've been using a bunch of results from the beginning, right? So start from the 23rd stream, the first tensor analysis stream, where we derive a bunch of equations for the summation notation, and now they're getting being used. So it's kind of difficult to follow if you don't know where this is from, right? But it's okay. We're gonna just keep pushing, okay? Because we will quote the previously proven result, but we're not going to prove it again, just for saving times. All right. So there's that, and the final example of this section says. It's the same setup, okay? You still have AI and BJ, the same setup. Example 18, same AI and BJ as above. Okay. Then you have Cij, which is defined as AI BJ minus AJBI. AJBI, this is also components of covariant tensor of the second order. I mean, as I said, I mean, I appreciate you call this a lecture. In a sense, well, what's the difference between scalar product and this outer product notation? This is a very big difference. Actually, let me finish writing that up. It's a big difference because here, the scalar product is a number. Here you have two free indices. If you write it as you can write this thing as a matrix. It's a product. I mean, it's a product between two tensors. For a scalar product, that's a contraction. The scalar product is, or the dot product is a contraction. Right? So this is not in itself an invariant. This is not in this. If this is in itself an invariant, that would be Cij bar equals C alpha beta without the Jacobian stuff. That's the outer product. All right. So anyway, let me just finish writing this up. So you get AJBI. All right. So I was trying to say that this is not a lecture, although the format sounds like one. Okay, I'm like a guy trying to write stuff on a blackboard. The thing is, I'm doing this as my own study process. You see, I get confused all the time. Right? This happens a lot in my stream, but I guess that's the point because I figure if I get confused, there's a chance that other people are confused about this as well. So might as well just show my confusion and see how I resolved it, so people can understand it better. Because if I just say present the whole everything as if everything is obvious, then it's not very going to be very useful, right? Because when you actually do learn this stuff, it's inevitable that you'll run into a wall at some point. So I'm just trying to do the job of locating, okay, where exactly do I get stuck, where I make mistakes? Is that just a silly mistake or there's actually something subtle going on? So it gives you perhaps a perspective, okay? It's okay that you feel confused. It's just a natural process. I mean, I guess, is this live? Yeah. This is live. This is not, I'm playing from a script, okay? I'm doing this in real time. Yeah. So I'm saying is this quantity is also covariant, second order. Let me just covariant, second order. And also, it's also anti-symmetric or skew symmetric. Yeah, it's totally okay to feel confused. I mean, even top tier mathematicians do that all the time. That's just completely normal. Um, uh, what we wanted to get from this experience is to locate where things are unnatural, right? Or things are hard to absorb. For example, the definition of tensor itself feels highly contrived if you don't know the context and the motivation. Right? So hopefully things are now easier to digest, but still, I mean, it requires a lot of practice to be comfortable with them. Right? This is not an easy subject, but we're just trying to make things doable. All right. So yeah, let's take a look at the and now we're ready to discuss geometry. How amazing is that? We're going to introduce the notion of Riemannian, Riemannian space and whatnot. But this section is called line element. Even now, I'm trying to maybe find someone doing linear algebra so that I can find a partner to solve problem. I mean, we can do linear algebra, no problem. We can do linear algebra, but I mean, I have a bunch of stuff need to finish. Actually, I plan to do I plan to do an advanced linear algebra. Yeah, no worries, no worries. The live is on the channel. The only thing that you're missing, XP transformation. The only thing that you're missing is the live interaction, right? like the recording is going to be uploaded. You can watch it anytime you want. But let's say if you're following me in real time and you spot a mistake, and that which will be fantastic actually. I appreciate a lot if that happens. When that happens, a lot of people do that in my previous stream. So the only part that you're missing is the live interaction. But still, you can still ask questions in the comment section. So yeah, go ahead and do your thing, obviously. Okay. Um, so right now we're in a position to introduce Riemannian geometry. Okay. So here, this section is called the line segment, the line element, the line element. All right. Okay. So in Euclidean space, you have this formula. Okay, cool. Okay, cool. Um, so yeah, um, Marco, I suppose your plan to do some, I don't know, relativity or continuum mechanics with this stuff. So in Euclidean space, we have the formula ds squared equals dx squared plus dy squared plus dz squared. Yeah, the OG calculus and analytic geometry from MIT is the best. Yeah. So actually, um, so once I'm finished with this stuff, which is gonna take a while, so probably mid-August, I suppose. Mid-August is like 2 weeks from now. I can do a what's that? I can do a dedicated live like this, just like the same format, or series of lives, probably going to be series, called Linear Algebra for Differential Geometry. It's particularly tailored to differential geometry, and it covers tensors from a modern perspective. Right? So without the indices, which I think will be a good complement of what we've done here. So engaging in casual sets here towards quantizing gravity one time. Wow, quantizing gravity, you'll get a Nobel Prize for that if you manage to do so. But anyway, still, um, it's good to have goals. So yeah, in Euclidean space, we know exactly what this means. And by the way, you know what? I just wanted to perhaps talk a little bit about what this means, because this, dx squared, dy squared, dz squared, even though they're kind of intuitive, perhaps it's good to clarify them a little bit. Okay, this just means small distance square. It's a small distance square. But to be more precise, it means given a meaning, given a space curve, will be a long path, yeah, for sure. Um, that's okay. Given a space curve x of t, y of t, z of t. I'm glad that there are physics people following my stuff. I think that's a great thing because I wanted to learn physics from, well, people who know physics too. So, given a space curve xt, yt, zt, right, and what's the arc length? Right, when t greater or equal to a, less than or equal to b, the arc length would be the integral from a to b. You can think of it as the speed times the time. I'll be heading out now. I've got to sleep. Sure. Thank you very much for staying this long. Actually, that's great. Awesome. Um, it'll be speed times time, and then you sum over that, right? So what's speed? Well, speed is just dx over dt quantity squared plus dy over dt quantity squared plus dz over dt quantity squared. So this is like the speed squared. and take the square root, you get the speed times dt times infinitesimal time. That gives you infinitesimal, not displacement, but rather distance traveled. And then you sum it over using the integral sign. So really, you can think of this as integral of ds. This is ds, and you can write, okay, ds squared symbolically as dx squared plus dy squared plus dt squared. So this is what it means. This is an arc length formula. All right, so we can rewrite this in a Kronecker delta symbol fashion. So you can rewrite this as ds squared is equivalent to ds squared as the Kronecker delta, delta AB, or delta alpha beta, dx alpha, dx beta, where you have coordinates is now, say, x1 all the way to xn instead of x, y, z. Okay, so the coordinates are now x1, x2, all the way to xn. All right, so there you go. That's the coordinate, and we have this formula. So let's think about how this transforms. Okay, so well, let's do that. Transformation, you got, say, can write x bar I as x bar I of x1 all the way to xn, as usual. So this way, dxi bar, right? dxi bar is d of x. Let me just put the Jacobian. This is upstairs, so dx bar over dx. D new versus d old. I upstairs, say alpha downstairs. Alpha downstairs and repeat it. All right, so you have that. Okay, so ds bar squared should be Kronecker delta alpha beta alpha beta Kronecker delta. Oh, actually, why don't we write the inverse transformation as well? So yeah, the inverse transformation. We've been using new equals old times something, right? We can easily write down the inverse transformation. So this will be dxi. Okay, what's dxi? Well, dxi is just dx bar. So here you use the forward Jacobian. To change old components to new components. So if you have new components on the right, you should use inverse matrix, which is d old over d new. D over d new, so you get dxi over dx alpha like this. These two are equivalent. Right? These two are equivalent. So let's substitute the old components dx alpha in here. So dx alpha into the dx alpha, dx beta into the expression of ds squared. So let's do that. Okay, ds squared is ds squared. You know what? Let's actually just put a, okay, just in case of confusion. Just in case of confusion that you regard 2 as a script. No, it's just that squared. It's ds squared. Okay. Perhaps later I'll be sloppy about this and stop writing the bracket, but right now we just want to be absolutely clear. This is not a upper index. Okay. This is just a you can, yeah, that's just square basically. Okay, and the delta alpha beta dx alpha. Well, dx alpha is this thing. Dx alpha, let's write that as d bar mu, and then dx alpha over dx mu. Okay, that's dx alpha, and then dx beta. Let's do dx nu, and then dx beta over d. Where's the bars? Sorry, here. There should be a bar here. My goodness, that's a big mistake. Okay, so there should be a bar downstairs. I mean, isn't the new coordinate? Yeah, you see, this is what we use in definition. But here, I wanted to get an expression of dx alpha. I want to write the old coordinate in terms of, the old components in terms of the new components. Okay, so I want dx on the left, and right hand side involves dx bar. So remember, how do you get dx bar? How do you get from new? How do you get new from old? You use a forward Jacobian, right? So to invert this relation, it's like solving a linear equation. By taking the inverse matrix, you use the inverse matrix. The bar you just put downstairs here, you mean this one? This is because it has to be the opposite as this one. Remember, these two form inverse matrices. Right? I use the forward Jacobian to bring the old to new. And now I want old in terms of new. That is from new to old. You use the the other Jacobian. So now bar is downstairs. That's it. Okay, so there's nothing mysterious going on. So dx bar new. All right. So here, well, what's that? Well, so let's write this as just a notation. Okay, we're just gonna write this as g mu new bar. You're gonna write it as g bar mu new dx bar mu dx bar new, where the quantity g bar downstairs mu new is, well, delta alpha beta times dx, hang on, might need a little bit more space. Okay, so delta alpha beta times dx alpha over dx bar mu times dx beta over dx bar new. Okay, and then you use the swapping indices trick. If you use the swapping indices trick, what you should get? Well, you can say you swap the beta to be alpha, but then again you get two alphas, right? You get two alphas, so the summation convention does not work here. So you have to write things explicitly. You see what I'm trying to say? Here you use the summation, use the delta to bring beta to alpha in this last factor. But now you have two alpha on top. But when you have two repeated indices, both up or both down, the summation convention does not apply. But still, this needs to be a summation, so you just have to write the summation explicitly. That makes sense. Okay, so does this gear towards general relativity theory? Actually, no. At least that's not the immediate concern. Right now, we're just, of course, it will be helpful because we're gonna get to curvature, and general relativity theory, of course, is all about curvature. We'll see if I have time for general relativity, but the immediate goal is to understand curvature, because curvature is just a much more universally more important notion. I mean, I'm not a physicist, and the immediate goal is I want to prepare for a session on information geometry, which is differential geometry applied to mathematical statistics. So yeah, but certainly this is a very good goal, and we'll see if we get to general relativity. Probably, I mean, I can't say much about general relativity because I'm not an expert, but at least I guess we could as a bonus of this series we can derive the Einstein's equation. We can derive Einstein's field equation, but perhaps not solving it and discuss its property because that's just get us too far. But it's still very. This is the fundamentals of um, of general relativity. What we're doing now. Okay, so as I was saying, like if you replace the coordinate index, you get two repeated upper index. But now summation cannot be assumed, so you just have to write the summation explicitly. So alpha goes from 1 to little n. It's just the way it is. Yeah. Seems like there's a lot of interest about physics too on the channel as well. I mean, this morning I was on this morning I was on what's the name? JC. Yeah. Do you guys know JC? I was on JC's stream, so he streams a lot as well. So he was a computer scientist slash pure math guy. Okay. I'm well, as you can see, I'm more of applied math and stats kind of guy. Of course, I do appreciate a lot of pure math. Actually, one of the goals of this channel, the meta goal of this channel, is to bring more cross communication, cross disciplinary communication. That's what I mean. But basically, I mean, I recommend you check out his stuff. JC practices math. So yeah. So why do I bring that up? Because I was saying there are people who recognize me in JC's stream that so man, you seem like you do a lot of subjects, right? Because I mean, even though it's meant to be a foundation, the formula is sufficiently enjoyable. Is sufficiently enjoyable. Hopefully, this is not too much suffering. Okay. Anyway, so yeah, I was saying like one of JC's viewers was saying to me that, wow, Ming, you do a lot of subjects, right? I was just saying that it's simply because applied math is so big, um, is so big, and I wanted to do as many as I can, basically. So yeah, if you guys don't know JC's content, go check him out. And he streams a lot too. So anyway, so I was saying, okay, so this quantity right here, which is super important, we're gonna give it a name probably. Yeah, we're gonna give it a name. Hang on. This is. Oh, thanks a lot. Thanks a lot. So this is a G bar mu nu, and not beta, but alpha. Alpha. Okay, this is alpha. Beta alpha. Okay. So yeah, this is the most general form of a line segment. This is the most general form of a line element. So far, remember, here we're still doing Euclidean geometry. This is Euclidean. This is Euclidean geometry. So we're still doing Euclidean space. So this is Pythagorean theorem. This is Pythagorean theorem. Remember, Pythagorean theorem is a property of the Euclidean space. It's not an artifact of coordinate. So of course, if you use different coordinate system, let's actually give an example. This is just the Pythagorean theorem. If you use different coordinate system, the Pythagorean theorem still holds. It's just that the g factor might be different. So the textbook don't give much examples, but let's take a look at some our homemade examples because I figure that could be helpful. Right. So why don't we do cylindrical coordinates? So this is old x, y, z. Cartesian. Actually, just write Cartesian. So Cartesian coordinates are x, y, z. And now you have cylindrical, and we'll do a polar coordinate. Actually, not polar, but cylindrical coordinate. Cylindrical coordinate, say r theta z. Okay, r theta z. So this is theta. Actually, first of all, x, y, z. Same z here. Okay. So okay. What would be the g here? What would be the g bar here? You must be cautious not to make the two derivative on the alpha and the second derivative. What do you mean here? Here. So I just want to give an example of this expression here. If that makes sense. So here, I mean, these are coordinates. These are Cartesian coordinates. These are actually Cartesian coordinates. Usually, in our previous discussion, x1 all the way xn are just arbitrary coordinates, right? Here actually means Cartesian. Because only in Cartesian coordinate you got the line segment equals dx squared plus dy squared equals dz squared. Okay, diagonal coefficients are all 1. The cross coefficients are all mixed coefficients are all 0. This is a Cartesian coordinate here. We're assuming the Cartesian coordinate. And now you have the coordinate transformation. So looking at this expression, this is d old over d new, right? So what's the relationship? Well, x equals r cosine theta. And y equals r sine theta. Now be always very clear about the meaning of these variables. Blind application always dangerous. It's always dangerous. Okay, so you have these quantities, right? And let's calculate d alpha over d mu d nu. Okay, I think that's a good thing to do. So you got let's do the matrix here. Let's do matrix. So you got dx over dr, dx over d theta, dx over dz, the first row, and then you get dx over dy over dr, dy over d theta, and dy over dz. Okay, and then dz over dr, dz over d theta, and dz over dz. Okay, what is this matrix? Well, it should be quite easy to calculate just from the transformation law. Not the transformation law, but the coordinate transformation formula. Actually, this is the inverse transformation formula. Maybe I should put it here. Okay, so there you go. The matrix is block diagonal cosine theta minus r sine theta 0 sine of theta. Actually, dy dr is sine of theta. Yes, sine of theta r cosine theta 0 0 0 1. Okay. So you have that, and now you do the calculation here. So what is G bar? I mean, not G bar, but um, the G. Should I use what notation should I use, chat? Right. This is Cartesian. These are xi's, and this is x bar I. X bar I. So my point is, how do you write? Okay. Hmm. The formula, the general formula ds squared equals g bar mu nu. These are the mu nu aren't coordinates. Okay, these are just labels. They're just indices. They're just indices. Okay, so dx bar mu dx bar nu. In general, this should contain 9 terms. In general, this should contain 9 terms. So you can see. Okay, but looking at this expression, you should have n terms here. Yeah, there should be n terms here. So we're looking at the no. That's a mistake. In this expression for ds squared, there are n squared terms, right? There are n squared terms because one sum is n terms. So now you have 2 repeated indices. So there should be n squared terms. There should be n squared terms in the expression with ds squared. And in each of these terms, there is this factor g bar. And each g bar, now that you're considering this individual term, individual factor g bar, it has 2 free indices, right? 2 free indices. If you fix particular mu and nu, you should have a sum. There's sum of n terms. M terms here, obviously. So right now I'm just trying to figure out this g here. Right? Right now I'm just trying to figure out this g. So you can think of x bar 1 as r, x bar 2 as theta, x bar 3 as z. Okay, x bar 3 as z. So if we write that, what should g look like? What should g look like? So g bar should have, in general, 9 of them. There should be 9 of g bars. Let's write them down separately. Okay, so g bar 1, 1. What is g bar 1, 1? G bar 1, 1, using this definition, is the sum of alpha from 1 to 3. Okay, so 3 terms. Just say 3 terms. Here we're dealing with 3 dimensions, 3 terms, and alpha. Okay, here alpha dx alpha over dx1, dx bar 1, dx alpha over dx bar 1 as well. Okay, so that's the application of this formula. So what does that look like? What does that look like? Well, x alpha from 1 to 3 is just x, y, and z. And x1, remember now x1 is fixed because of the x1, and x1 are fixed because of the subscript of g bar 1, 1. And x bar 1 is what? It's just xr. So that's just dx over dr times dx over dr plus dy over dr times dy over dr plus dz over dr over dr. Right? Just want to keep everything concrete because these formulas can easily be quite confusing. But this is what explicitly this means. Right? Dx over dx, as we just said, is a cosine square. It's just cosine squared theta plus sine squared theta. dz over dz partial derivative is dz over dr partial derivative is 0. So you just get 1 here. So g bar 1 1 is 1. Okay, and continue. What is g bar 1 2? G bar 1 2. Well, that's the sum alpha from 1 to 3 dx alpha over dx bar 1 times dx alpha dx bar 2. Right? So there you go. What does that mean? Well, that's just dx over dr times dx over d. What is x2? x2 is theta. dx d theta plus dy dr dy d theta plus dz dr dz d theta. Right? Just want to be extremely clear what this g bar stands for in this setup here. Okay, so yeah, let's do that. Dx dr is cosine theta. Dx d theta is minus r sine theta plus dy dr, that's sine theta, times dy d theta, which is r cosine theta, which gives you 0. Which gives you 0. See, dz dr and dz d theta are both 0, so this is just 0. Is 0, okay? So g bar 1 2 is now done. Okay. By the way, it should be clear that g bar mu v is symmetric. From this definition, it is immediate that g bar mu v equals g bar v nu. Sorry, not nu v, okay? Mu nu. My goodness, this is mu nu equals g bar and nu mu. Right. So this saves us some work. We just need to calculate 3 terms. Actually, not 3 terms, 6 terms. We need 6 terms. That's enough. Okay. Next up, this is g bar. Okay, just to emphasize symmetry, this is g bar 2 1 as well. Okay. And then let's do g bar 1 3. What's g bar 1 3? That's the sum over alpha 1 to 3 dx alpha dx bar 1 dx alpha dx bar 3. Okay, write that down explicitly. You get dx over dr dx over dz plus dx over dy over dr dy over dz, and finally dz over dr and dz over dz. But each term in the summation is 0. See, dx dr is 0. Actually, dx dz is 0. This is 0. dy dz is 0. And dz dr is 0. So nothing going on here. That's a 0. And this is by symmetry is also g bar 3 1. So there's only two more diagonals and one more off diagonal. So the next diagonal element is g bar 2 2. Right, do the same business. Alpha 1 to 3 sum. Then you get, think about what's that mean. Think about what that means. Okay, so still dx alpha over d, what's the second variable? Second variable is theta. Dx alpha over dx bar, or not dx bar 2, yes, dx alpha over dx bar 2, second variable, and then you get, this is dx over d theta, dx over d theta plus dy over d theta, dy over d theta plus dz over d theta, dz over d theta. Okay, cool. So dx over d theta squared is r squared sine squared theta. dy over d theta squared is r squared cosine theta squared, which is just r squared. Okay, so that's the other diagonal elements. And finally, not finally, there's the last off diagonal element, that's g bar 23. What's g bar 23? G bar 23 using the formula is the sum alpha 1 to 3 d, okay, x alpha over the second variable dx bar 2, and then dx alpha over dx bar 3. Okay, that's a 2, not alpha. Okay, that's a 2. So what would that be? It would be dx over d theta dx over dz plus dy over d theta times dy over dz plus dz over d theta times dz over dz. Once again, every term is 0. All three terms are 0. Dx over dy is 0, dy over dz is 0, dz over d theta is 0. So the sum is just 0. And last but not least, actually this is also the same as g bar 32. Last and not least, you have g bar 33. Okay, so that's the sum over alpha 1 to 3, dx alpha over dx bar 3, dx alpha over dx bar 3. Okay, so once you simplify that, you get dx over dz, dx over dz, dy over dz, dy over dz, and dz over dz times dz over dz. Of course, this is just 1. Okay, so now all 9 terms are obtained, and there's only 3 non-zero terms. So according to the ds squared formula, right here, this one. So the ds squared formula in cylindrical coordinates, according to this formula, is what? Oh, you just pick up the terms where g bar mu v is non-zero, mu nu is non-zero. Okay, so therefore, in cylindrical coordinate, you get what? According to a non-zero term, that's g11 bar dx bar 1 dx bar 1 plus g bar 22 dx bar 2 dx bar 2, and finally g bar 33 dx bar 3 and dx bar 3, which is what? Which is 1 times dx quantity squared plus, you see, if I don't use bracket, this looks like an x2, which can be easily confused with dx bar 2 above. So that's why we use a quantity bracket here. So anyway, and g bar 22 is what? G bar 22 is r squared times d theta quantity squared. Oh, actually, x bar is r. My bad. This is r. dr. Okay, and finally, this is just 1 times z squared. Okay, so that's it. Does that make sense, though? Does that make sense? It does make sense, right? It does make sense. So looking at this little infinitesimal rectangle, for example, we can call it that way. This is dr, right? And this is the d theta, r d theta. And then you have an infinitesimal change in z. So basically you have this approximate rectangle, and the so-called ds squared is the body diagonal length squared. So d is dr squared, okay, times r d theta squared, and then d plus dz squared. So this is still Pythagorean theorem, but just expressed in a different coordinate system. So even though the G here is not Kronecker delta, right? This is not Kronecker delta. The geometry has not changed. This is still the Pythagorean theorem, the usual Pythagorean theorem in Euclidean space. Okay, so um, so therefore, the most general form for the line element, the most general form of the line element ds squared for Euclidean space is the quadratic form g g alpha beta. Is a g alpha beta d alpha d beta. Okay, so let's conclude that. Okay, thus, hence, the most general form for the line element for a Euclidean space is as follows. So you get ds squared equals g alpha beta dx alpha dx beta, as I just said. Okay, and the g alpha beta are components of the metric tensor. Second order covariant. So that's a component of the metric tensor, and we did the example earlier to verify this is indeed a tensor, which is example 15. Oh, dz squared, yeah, dz squared, here, dz squared, exactly. Yes, Marco, thank you very much for being careful. Yeah, dz squared. Right, here I just, of course, yeah, this example, I hope everyone is on board about what this is about, okay? It's just a application of this formula. In the general setup here, we started from the Euclidean space, okay, n-dimensional Euclidean space, and assume there's a coordinate transformation. Coordinate transformation, the new coordinates are barred coordinates. Okay. ds squared is a quadratic form in dx bar. Okay. And g bar has this formula, and we just verified this. Which agrees with our intuition in regular calculus. So everything is okay. G alpha beta is a component of a metric tensor. See example 15. Okay. So the quadratic form, this is called a Riemannian metric. Okay. So this equation, which we call 498, is the label in the text. So 498 is called a Riemannian metric. This is called a Riemannian metric, and any space equipped with any space, let's say, any space whose line element is defined by 498 is called a Riemannian space. A Riemannian space. I mean, Riemannian space is perhaps a little bit vague because nowadays you speak of Riemannian manifold, but to do that you need to define manifold formally, which we're not going to get into in this series. So basically, you can think of a set whose neighbors, whose neighborhoods everywhere is roughly Rn. So it's like in a set, and you select the neighborhood and you zoom in close enough, it looks like Rn. It looks like Rn. So that's a rough definition of a manifold. So you just need this flatness, this local flatness. That's enough for describing a surface, right? Think about your everyday experience. We know the Earth is a sphere, or roughly, but to our everyday experience, it appears to be flat. Right? So that's the idea of a manifold. But here, a manifold in itself can have very few structures. Okay, just like in vector space. And when we talk about vector space in linear algebra, the bare vector spaces on its own just has two operations. Right? Just has two operations, namely addition and scalar multiplication. And now you can define other structures on it, such as inner product. And certainly you can discuss more geometries there. Okay, and that's the same idea about the Riemannian geometry. So in a general smooth manifold, okay, or a general manifold, in a general manifold, you only have this property called local Euclideanness. Okay, that is to say, if you zoom in close enough in any neighborhood, it looks like roughly flat. But it doesn't say, okay, what does the distance behave and whatnot. It doesn't say that. Um, Here we say you have this extra property that if you zoom in close enough, then the distance, the line element is given by this. Okay, so let's just call it that way. So locally, the line elements are given by this quadratic form. So that's a pretty informal definition of a Riemannian space. Okay, so but that's good enough for us now. Okay, so here this is called a Riemannian metric. 498 is called a Riemannian metric. So because this is a general form for the line element, remember sorry, what's that? What is G alpha? G alpha beta. That's a symmetric matrix. You can think of it as elements of a symmetric matrix. We don't know if this can be written as a sum of squares. In Euclidean space, you can always do that. In Euclidean space, you can, for example, if let's say you start from a cylindrical coordinate, you can still convert the cylindrical coordinate to Cartesian so that the expression for the line element is a sum of squares. It turns out you cannot always guarantee to do that. Okay, there's no a priori guarantee. For a general G alpha beta, there's no guarantee you're going to change this to Kronecker delta. Remember, if this is a sum of square, then G alpha beta is a Kronecker delta. It does not follow that you can always do that. So 498 is called a Riemannian metric if there exists a coordinate transformation, if there exists a coordinate transformation such that xi equals xi of y1 all the way to yn, such that the ds squared, which equals, well, 498, it can be converted into Kronecker delta alpha beta dy alpha dy beta. So if you can convert the formula into this one, then we say the Riemannian space is Euclidean. So 498 is called a Riemannian metric. a space equipped, quote unquote, this is very vague, okay, equipped with a Riemannian metric, or let's call it R metric. It's called a Riemannian space. Our goal now is to, our new goal, okay, grand goal is to study the geometry of Riemannian space from the metric tensor. So now the metric tensor is the primitive object here. Okay. The Euclidean space is the special case in which Euclidean geometry, okay, Euclidean geometry is a special case in which the formula for the line element can be written as such, as a sum of squares of new coordinates. Okay. If there exists such a coordinate transformation that turns ds squared equals a sum of squares, we say the Riemannian space is Euclidean. All right. Okay. Um, and of course, the yi's will be the components of Euclidean coordinate system. Okay. So, as we mentioned, we can choose the G to be symmetric. We can choose the G to be symmetric. So we'll assume that from now on. Okay, assume G is symmetric. So now let's take a look at some examples. Assume G alpha beta is symmetric. Okay, assume G alpha beta. Let's look at an example here. So this example is a spherical coordinate. So let's say you have ds squared originally. Okay, ds squared equals dx1 quantity squared plus dx2 quantity squared plus dx3 squared. All right. So Cartesian spherical coordinate x bar 1, x bar 2, x bar 3 are defined as follows. R theta phi equals R theta phi. Now, just regular multivariable calculus stuff that should be familiar. All right. So R is the distance of a point to the origin. x1, x2, x3. How did it appear that Kronecker? No, it says if there exists a coordinate transformation so that you can write the ds squared to be this way, then we call it Euclidean. Remember, we started from the Euclidean as a motivation, right? As a motivation for the definition of Riemannian metric, we started from the Euclidean distance. No. There's no derivation here. So here earlier we said, okay, if you start from a Euclidean, the usual Euclidean geometry, the Cartesian coordinate system. Of course, Cartesian coordinate system is not special. Okay, it's not special at all. It's just that in the Cartesian coordinate system, the Pythagorean theorem is written as a sum of squares, and hence the Kronecker delta symbol. This one and this one are the same thing. It's just that it says in the Pythagorean theorem is a property of the Euclidean space, nothing else. And using Cartesian coordinate, the Euclidean space line element, or line element is a sum of squares. And this is an artifact of the Cartesian coordinate system. This is an artifact of the Cartesian coordinate system. What we're saying is this is a particular choice of coordinate system. And in that choice of coordinate system, you have your line element being able to be written as a sum of squares. Right? And let's say, what if you don't use Cartesian, right? Let's say if you use an arbitrary coordinate x bar, then ds squared should be in this form. Then, so the coefficients for the quadratic form may no longer be Kronecker delta. Does that make sense? So we take that as our inspiration. So we take that as our inspiration and define the Riemannian metric to be in this general form. So G alpha beta is a general symmetric. It's a general symmetric and also believe positive definite. Okay, because in Riemannian metric we don't accept negative distance. Okay, so there's that. We don't accept negative distance square. In special relativity, however, you can do minus, but still, I mean, I think I'll double check. Okay, to double check to see if G alpha beta can be associated with a quadratic form that takes negative values. Okay, so the indefinite situation. I'm not sure if you can do that, but as of now, this form is called a metric tensor, in which G alpha beta is symmetric. And a space, a quote-unquote space being equipped with this formula to describe its line element is called a Riemannian space. Okay. Once again, I emphasize this is not the modern definition. Okay. But that's not the point here. Okay. Locally, if the lines have lengths given by this formula, we call it a Riemann space, a Riemannian space. So when is a Riemannian space Euclidean? When is a Riemannian space Euclidean? Right? You can't tell that from the G alpha beta itself, because G alpha beta is coordinate dependent. So we say the space is Euclidean. The space is Euclidean if G alpha beta, okay, can be transformed into a Kronecker delta under some coordinate transformation. If you can transform it into a Kronecker delta, that is to say, if the line element expression can be written as a sum of squares, if it can be written as a sum of squares, it's a linear algebra problem, by the way. This is a linear algebra problem. It has to do with the eigenvalues, eigenvectors of G alpha beta. If it can be written as a Kronecker delta, then the space is Euclidean. Okay, I know this is a very convoluted definition, but hopefully, you know what? Perhaps this is all feels very abstract, right? Let's just take a look at some good old linear algebra to get a hang of this, right? So in classic linear algebra 2, we have this application of orthogonal matrices. We have this lesson on quadratic form. Maybe most of you guys have already seen that. So this is a general quadratic form. Of course, in a general quadratic form, you got these diagonal elements. So we wonder if you can transform the coordinates so that the quadratic terms can be eliminated. And it turns out you can always do that. You can always turn that into a diagonal matrix because Q is associated with a symmetric matrix. It's a symmetric matrix. It is a fact that symmetric matrices are always orthogonally diagonalizable. It's not only diagonalizable, it's also always orthogonally diagonalizable. You can always do that. Okay. You can always do that, but it's not clear whether you can turn it into a Kronecker delta. If that makes sense. So here, the diagonalization guarantees you can write it as a sum of square, but Kronecker delta requires all the lambdas to be 1, remember? All the non-zero lambdas to be 1. That would be a Euclidean space. You can diagonalize, namely you can remove the cross terms, but it is not always guaranteed that you can have just squares on their own. The coefficient has to be 1 here. So for example, here you see you got this a quadratic form in 4 variables. So imagine this is a metric tensor. So you can imagine this is a metric tensor in some 4-dimensional curved space locally. All right, and then what you get? Oh, look at the diagonalization. Look at the diagonalization. Well, these are all squares for sure. These are all squares for sure. The positive elements, you see, the positive ones can be turned into pure squares, right? Because here you can just do another transformation and say 12y1 squared is y prime squared. So this way, this becomes a pure square. And you can do the same for y3, y4. However, there's a sign difference. There's a sign difference. For Kronecker delta, all the coefficients must be 1. You can scale y1, y4, y3, but you cannot scale y2 so that its coefficient is 1. You can never do that. So even though this is a Riemannian metric, it is not a Euclidean one. So the space, you see the space, by a transformation of coordinate system, it can be written as such, but this is not Euclidean. This is not a Euclidean metric because of the minus sign that ruins the party. Okay, so that's why I'm saying it is not always possible to rewrite a quadratic form whose coefficient is a Kronecker delta. But if that's the case, then we say Riemannian space is Euclidean. So because now your yi's, y1 all the way to yn's, are just Cartesian coordinate axes, not Cartesian coordinates. So that's it. Right? So that's the definition of Riemannian space. Okay, from a purely computational perspective. All right. So let's take a look at this example here. So consider the spherical coordinate x1, x2, x3 equals r, theta, and phi. What's the transformation law? So what's the transformation of coordinates? Okay, so first of all, let's draw the picture. Here, this is r. This is r, and let's define the r and theta. Interesting. Never seen in perspective from my linear algebra lesson. Oh, by the way, if you guys are interested in the diagonalization, this is a basic linear algebra. Okay, it's a basic linear algebra, and I think this should be known to everybody following the series. Okay, or just whoever seriously studied linear algebra should consider quadratic form an essential part. Okay, so let me just put it in chat. This is a good resource. It's got free video, it's got like video lessons and whatnot. Pretty easy to follow. Alternative format is like the notes, okay, and this is the video. So yeah, go check those out. As I was saying, not every quadratic form can be turned into one with Kronecker delta coefficient. It's not always possible. But if that's possible, then we call it Euclidean. We call it Euclidean, all right? So now we have this definition. Let's take a look at the transformation between Cartesian and spherical coordinates in Euclidean space. So once again, we already know it's a Euclidean space. So whichever formula for ds squared in terms of the spherical coordinate should be able to be transformed back into the usual Cartesian form. You should be able to do that. We know what to expect, but just see how that's carried out. Okay, so, all right. So here you have the, what's that? This is a three-dimensional Euclidean space, and of course, here in this formula, you can write it as delta alpha beta dx alpha dx beta. Dx beta, all right? So this way the G matrix is just 1, 0, 1, 0, the identity matrix basically. All right, so now let's consider spherical coordinate. Spherical coordinate, well, we gotta, let's first give the transformation between Cartesian and spherical. x1, x2, x3. All right. Oh, my goodness. I'm getting tired. Hang on, let me see how many stuff are in here. Okay, we might not be able to finish that today, but finish the section on line elements today, can we? Actually, we cannot. I'm getting a little bit tired. I will take a little break. Not now, but after this example, I'm just gonna call it today, and we'll continue tomorrow. Yeah. So we're here in the meat and potato of tensor analysis. So we're now deep in geometry territory. Okay, not just messing around with notations anymore. So okay. Anyway, so I was saying that this is the line element. Metric tensor. Is more appropriately called a metric tensor component. The metric tensor components in the Cartesian system, okay, Cartesian coordinate system, okay. And now the spherical coordinate system. Let's just recall from multivariable calculus how does it relate to the Cartesian coordinate. So first of all, r is the distance between a point and the origin, and then you're going to take the angle between the radial vector and the z-axis, namely the x3 axis, x1, x2, x3, all right, and call that angle theta, right? This is theta. All right, and then you consider the foot of perpendicular of the point onto the x1, x2 plane. x1, x2 plane, and that point, when connected to the origin, makes an angle with the x1 axis, and that axis is called phi. That's called phi, all right? So once you have that, you get x1 is r times sine of theta cosine of phi. x2 is r sine of theta sine of phi. Just from basic trig relations, all right? And x3 is r cosine of theta. x3 is cosine of theta. So now you're just going to do the same calculations that we did earlier for the g bar. Remember how we calculated g bar for a cylindrical? We're going to do the same thing. All right, so g bar is what? Comprehensible, so much lessons these days. Comprehensible. What do you the markup like? What do you mean is? I guess so. You're on board with this definition. Is that what you're saying? Okay. If that's okay, then we can move on. So what I'm saying is you have G bar ij. G bar ij by our definition is G alpha beta. Right? G alpha beta. G alpha beta, by the way, is just the Kronecker delta here. Okay. And then dx alpha over d. You're being tired. Yeah, I am a little bit tired. Okay, sorry. Okay, so this is x bar x bar. What's the notation here? X bar. Yeah, x bar. What notation? I. Yeah, x bar. No, x bar I. And then dx beta over dx bar j. All right. So that's the formula. But because of the G alpha, beta is just the Kronecker delta here. G alpha beta is the Kronecker delta. You just got three terms here. That makes things a lot easier. You just dx1 over dx1 over dx bar I, okay, and then dx1 over dx bar j plus dx2 over dx bar I dx2 over dx bar j. And then plus dx3 over dx bar j, x bar I, dx3 over dx bar j. Okay, so these are the terms we need to evaluate. And of course, you can use the actual names for the barred coordinates. Right? So this is just dx1 over dr. No. We're not picking specific ij's here. My bad. My bad. No, you have to do that for specific entries of gij. Okay, so let's do. Well, we'll finish this calculation and I'll call it a day. So g bar 1 1. G bar 1 1. That's just dx1 over d x bar 1, which is r. Dx1 over dr. Yep. Dx2 over dr, dx2 over dr, finally dx3 over dr, dx3 over dr. All right, so there you go. You got everything we need from the transformation formula. So the first one is just sine of theta cosine of phi quantity squared. The second is sine of theta sine of phi squared. And lastly, you got cosine squared. Cosine squared. So together, this is just one. Yeah, this is just one. So that's simple. G11 bar. And then, G22, G22 is what? G22, diagonals, G22 bar is, so you're gonna, just gonna copy things, okay? So just to save some writing, change all the r's to theta. Yeah. Change all of that to theta. Okay, this way you get G22. Hold on a second. That's what. Right, this way you get r squared cosine theta. Actually, r cosine theta cosine of phi, quantity squared, plus minus r cosine theta sine of phi, quantity squared, and then plus finally r minus r sine of theta, quantity squared, and that is r squared. Yeah, that's r squared. So there you have that. And lastly, the last diagonal elements. Okay, the last diagonal element is g bar 3 street. G bar 3 street, which will be okay, very much the same expression, but the last the downstairs variables are now phi. Okay, all right. Okay, here we go. dx1 over d phi. What's that? dx1 over d phi. That's r sine theta minus sine phi. Put minus sign to the front. Okay, quantity squared. The second term, dx2 over d phi, that's r sine theta cosine of phi, quantity squared. And then plus 0 squared, and you get r squared sine square of theta. Sine square of theta. So these are the diagonal elements. And you also, I'm not gonna repeat it because it's kind of tedious, but you can check that. Okay, I'm getting lazy, okay, but because I justify my decision of being lazy by pointing out I already calculated the cross terms exactly the same way as earlier for cylindrical. So you can easily repeat this process, okay? And at least if you don't want to actually calculate everything, at least write down the expressions to make sure you understand what g bar comes from. Okay, what g bar comes from. And I cannot stress it enough. I cannot stress it enough because of the derivation. Because of the derivation, this formula for g bar, this formula for g bar only works when the upper stairs variables are the Cartesian coordinates. This expression for g bar mu v is rather special. I mean, you can even argue this is not even important at all. But as a computational example, it is good that you can work it out, the details. So this g bar has nothing special at all. There's no profoundness going on here because here we're choosing the Euclidean space and the Cartesian coordinates and transforming it to a different set of coordinates. It's a useful computation tool, but there's no significance here because this is a very coordinate dependent formula. Upper stairs is Cartesian, lower stairs is a general one. Okay, so anyway, so we can check that for the spherical coordinates, the g bar ij is 0 for I not equal j. Okay, this is left as exercise. And you can combine all these terms and finally you get ds squared. ds squared is 1 times dr squared plus r squared times d theta squared, and finally r squared sine squared times d phi squared. All right, so this is a line element in spherical coordinate. line element, spherical coordinate. The coordinate is spherical, but the underlying space that it models is still Cartesian. Not Cartesian, but Euclidean. Namely, this is just a statement of the Pythagorean theorem in a different set of coordinates. Line element in spherical coordinate. Okay. In the Cartesian coordinates, the coefficient has to be constant. Here, it's not constant. Okay, so why don't we just call it a day? Because I'm getting a little bit tired, and next time we will see more examples, including a fun one. That's the special theory of relativity, the Lorentz transform. The Lorentz transform. We'll see that next time. Okay, and this will give us an example of a non-Euclidean space. Okay, so this will give an example of non-Euclidean space, and at this point, and we'll also introduce a notion of geodesic, and the notion of geodesic and the Christoffel symbol. Okay, so next time, to be continued. We'll talk about the Christoffel symbol. How do you even spell that? Christoffel symbol. This is going to be exciting. No worries. Okay. I'll upload the notes later tonight. By the way, you can see all the notes. Do you guys know that? If you go to the past live streams, the top comment, the pinned comment by me, gives the link for a Google Drive that collects all the notes so far. Next, to be continued, we'll talk about Christoffel symbol geodesics. That's the path of the shortest distance in Riemannian geometry. It's pretty cool stuff, in my opinion. And the reason it's called a Christoffel symbol is that it's not a tensor, actually. This is an example of what we later call an affine connection. Yeah, that's great. Awesome. So you know where the nodes are. All right. So that's it for today. Thank you very much for watching.